So I'm Sergio Saniadevich. I'm the principal investigator of the Bridges 2 project. Welcome to the Pittsburgh Supercomputing Center. As you see here, we've been in business since 1986, and we do a lot of cool things, among which is the Bridges 2 project, which I guess most of you are familiar with because you are part of the Bridges 2 community. That's whom we, I guess, extended this invitation to. And I'm privileged to welcome you guys on behalf of the Bridges 2 leadership team here. I think a lot of us are in attendance. Robin certainly is. But welcome, folks. We are very privileged to have you. So this is part of our Bridges 2 webinar series that we're basically kicking off in this bright new year of 2023. And as you see, we intend this to be a forum for the Bridges 2 community to learn and share ideas and achievements, both in terms of work that folks have done and ideas for things to be done in the future. And that's both for people who are actively using Bridges 2 and for people that we might invite to share their thoughts with the Bridges 2 community, such as today. So we would very much like you to collaborate with us in suggesting future speakers, whether it is from your own team or others that you think would be useful in terms of what you're doing or what you think folks should be doing. Speakers, topics. So for now, just email me, and that's my email address over there. And we'll work with you to set up future webinars. So with that, it is my privilege to introduce today's presenter, Dr. Khemraj Shukla. Raj received his PhD in computational geophysics, and his work is, as you see here, common thread is high-order numerical methods. So his PhD was at Rice, and now he's an assistant professor at Brown. And without further ado, we'll ask Raj to take it away. Now, one note here, we would ask you to, so there'll be a Q&A session at the end after Raj finishes his presentation. We invite you to drop questions into the chat, and Raj will answer maybe some of them, if not all of them, at the end of his presentation, the ones that and he will indicate if there's an opportunity to answer other maybe more intricate questions later on in direct conversation with the questioner. So with that, Raj, please take it away. Thank you very much.
Thank you, Sergio, and thanks for your invitation. I'm really thankful that so many people attended and they have shown the interest. So let's start with so this work is in different components. So the first components is like the first implementation of parallel physics informed neural network is already published in the Journal of Computational Physics. And this work is still ongoing. So we are just doing into the pieces like for what problems these kind of methods will be effective. So this is joint work with Dr. Jagtap and Professor Karniadakis at the Brown University. And the main motivation behind this work is so existing the parallel programming environment for neural networks are based on the two approaches. So the first one is a data parallel approach. So it's very simple algorithms, and these algorithms and the codes are readily available in the deep learning frameworks such as the TensorFlow, PyTorch, and exclusively from the Horoward. The Horoward has a TensorFlow and PyTorch API, so you can directly take them and use this kind of algorithms, which is data parallel. So just crux of this algorithm is that what you have, like you take data and split into the number of processors which you want to use, are co-processors like GPUs. And suppose you have a data and you want to split into the 4 pieces because you have a 4 GPUs, and each GPUs will have same neural network model. This has to be noted that the neural network model should not change. So, and after that, what happens? Each GPU computes their loss function, and now this loss function are different because these data are the pieces of the main data. But in one GPU training, this loss function should be the unique. So what happens? Then there is a all reduce APIs of MPI, which is used in these implementation. Suppose GPU1 will collect all the gradient of the loss function with respect to weights and sum it and average it over, and then again broadcast it to all the GPUs in the communicator world. So in that way, what happened? Your gradient of the loss is the same. So that means your weight will be the same when you do the SGD or ADAM based update or LBFGS. And in that way, like you are training the same model, but on the different piece of the data. This approach is called data parallel approach. The one drawback of this method is that your neural network model should be the same. So like, suppose you have a 10 depth of the neural network is the 10, so it should be the 10. If it has like 300 neurons, then it has to be 300 neurons. So for larger model, this method may not be viable, like very large model. So there is another approach which is called model parallel approach. It's pretty much based on the pipelining approach in the parallel algorithms. So what you do, you take a batch and again split into the micro batches. And before that, at each GPU, you will have each layer of the neural network. And further, you just split your batches in the micro batches. The first batch goes to the L1, the first layer, processed by GPU1, and then it is further processed to the L2. That is during the forward pass. And then by the time the first micro batch goes to the L2, the B2 will be ready and it will come to L1, and then it will be processed in a pipeline approach. So similarly, we go for the backward pass. So in that case, whatever we do in the model panel, but we still have some pipeline bubble, which usually because the L1 has to wait, because by the time L4 is completing its first micro batch, L1 will has finished all the forward passes for all the micro batches. So there are some bubbles. So the idea of this the slide is that can we do better for the scientific machine learning except these two models? So in recent years, if you know that our group has done a lot of work on the PINNs, which is physics informed neural network. So that is basically the neural network based solver to solve the PDs and do the inverse problem. And after a few years of the development, there were two methods proposed by other researchers from the same group, like cPINN and XPINN. The idea is pretty much similar to the domain decomposition or discontinuous Galerkin method. Idea is like borrowed by those conventional methods. So can we use PIN plus domain decomposition to get rid of two existing the data parallel approach, which will resolve the issue of having the similar model on all the GPUs, and the pipeline approach like model parallel approach. So the outline of my talk is as follows. First, I'll describe what is a PIN and cPINN and XPINN, then parallel implementation. And then what we are doing here this is very large computation-based large eddy simulation modeling as an inverse problem. So we have almost done 90% of the work, but there are some validation is still left. So I'll tell that how hard that model was to compute. So just give a brief background on the physics-informed neural network. So that work was published in 2017 by Navier-Stokes and Professor Karniadakis. And in that, suppose you want to solve a PD. So suppose this is the PD. This is the time-dependent, the initial boundary value problems. So, and this is like a typical Burger's equation which you want to solve. So you have a network, neural network, for which the feature is space and time, because the PD depends on space and time. And then you do the affine transformation through the neural network, apply the nonlinearity, you get something out of the neural network, U. So if U is the solution of the PD, so then U should satisfy the PD. So what we do, we just plug U back into the PD and compute the residual. So when you put the approximated solution in the PD, so that becomes residual and that has to be 0. But you can ask, how do you compute the gradient? So the gradient, since with the advent of this deep learning framework, we have a very specific module called automatic differentiation, which is the basically automatic differentiation. The whole purpose of that method is to have a computer code which computes the derivative of the original computer code. So you have a suppose addition, as which suppose you have a subroutine addition, and there will be another subroutine which will compute the derivative of the addition. So it's basically the code generation for the derivative of any subroutines. So that we can use to compute the this derivative involved in this PD. But what would be the data? What is the data? So this PD will have a unique solution for a given boundary condition and initial condition. So this will be our data. And to compute the residual, we can put a lot of random points in the domain, space-time domain, and can satisfy this PD. And all these three are added as a loss function. And then you do the typical gradient update and optimization-based approach. You use a derivative-based gradient or the quasi-Newton gradient. And then you recover the weights and bias for this neural network. So in nutshell, so your loss function is basically contains two parts. One is the data, which is marked in the blue. So data is here for solving the PD is our initial and boundary condition. And the red with the loss function, which we call the residual loss, this is basically the residual of the PD computed at random points in space-time domain. So this is the whole idea of PIN. So basically what we are doing here, we are adding a regularizer term in the data loss. So this PD behaves as a regularizer for any loss function. So in that way, we can compute the solution and we are constraining the solution by and it is always added as a soft constraint, not as the hard constraint. There are other work also where they do the hard constraint also, which they satisfy directly that this neural network is solution of the PD. So this is just a recap, that the brief about the PIN. There are some limitation for the PIN, like it's optimization based approach, unlike FEM and the finite difference or finite volume. So here we try to recover the weights and bias of neural network through optimization optimizer. It could be the first order optimizer like ADAM, which is very famous, or the second order like quasi-Newton or LBFGS based algorithm. So the first is a large training time. It takes a lot of time to converge. And for that, we can have some approach based on domain decomposition strategy. And the second is due to high dimensional non-convex optimization problem. So what does this mean actually? So suppose you want to compute solution of a PD, which is U star, which exists. Now you have a finite data points and you have an optimizer, which is based on this finite number of data points. And that is HM. So that means HM is a class of the function which optimizes the loss function and finds the global minima with finite number of data points. But that doesn't exist because our function is non-convex. And so you just do a lot of engineering trick like play with the learning rate, scheduling the learning rate, and you get some HM hat, which is close to the HM, which is ideal. And there is another optimizer, which is H hat, which is optimizer for optimizing the loss function with infinite data points. So there are three errors: optimization error, estimation error, and approximation error. So optimization error is not well understood. So when you add estimation, approximation error, that becomes the generalization error. So here we struggle a lot to control the optimization error. So that's because we don't have ideal optimizer which gives you the global minimum. So there are a lot of work going in this topic also, but we are not going to discuss this today. So that could be the talk for another day. But here we are going to address the first point, reducing the training time via domain decomposition. So first, I did a profiling, like where you spend a lot of time to compute the solution using the PIN. So as I mentioned in the 2 slides before, that you compute the data loss, residual loss, and backward pass. So when you compute the residual loss, that means you are taking the derivative of the output of the neural network with respect to input. They are very high dimensional. So automatic differentiation, which we use, that takes most of the 95 to 96% of the time. So you can see that effect of that computation is so large that the computation involved in data loss and residual losses, backward pass is insignificant. So while computing the residual loss, you have more compute time which you take to compute the derivative. So this first plot is basically x-axis is the number of residual points and the y-axis is the runtime for 100 iteration. So if you increase the residual points, so increasing the residual points, you can understand it as increasing the number of cells in a finite element method. So if you have more residual points, that means you have more accuracy. So as you see that this grows proportionally as you increase the number of residual points. The second plot, the middle plot, is basically the number of layers, and x-axis is the number of layers and y-axis again the computation time. That again, the automatic differentiation takes substantial amount of the time. And the third plot is that x-axis is the width of neural network, that how many neurons in each layer we have. So again, so number of neurons. So that all these 3 plots say that more than if there is a more number of edges and nodes you will have in the computational graph, you have to spend more time in computing the automatic differentiation because of the nature of high dimensional output. So the idea for the domain decomposition is very similar to the conventional approach of domain decomposition. You take a domain and split into the subdomains, and in each subdomain you deploy the PIN. But what you do at the interface, so because solution has to be unique at the interface. So like in this continuous Galerkin approach, you have to stitch the solution across the interface through fluxes. So if we make the flux continuous along this interface, that means solution will be unique. So that is the one approach which is also known as cPINN, that's conservative PIN. So for conservative PIN, the flux has to be continuous. So if you want to write again this loss function for this domain, which is split into the number of subdomains. So you have a data loss like in the PIN, you have a residual loss in each domain, and then you have interface loss, which is basically to compute the solution across the interface. What is the difference? Because in order to have this solution unique, so you require the weights and bias has to be same. But there is indirect imposition of the flux, which will make the solution continuous. And for that, you don't need any weight and mass similarity. So this domain decomposition approach has this the 4 points which are addressed very well in the numerical network to compute the solution of PD, the parallelization capacity. So you can see that each subdomain can be deployed on each GPUs, and you have to do the only point-to-point communication, not collective, to compute the solution at the interface. And representation capacity. So if you see the PD, so not all the domain, not the entire domain have the same regularity of the solution. Somewhere it is discontinuous, so you need better approximation, like more number of layers. Somewhere it is very smooth, you just need few hyperparameters to resolve this. So accordingly, if we know some regularity of the solution, we can design the effective network. And in that way, again, this efficient hyperparameter adjustment is the product of representation capacity, because in that way, like you can choose how many layers and how much deep and how much wide your network should be according to the regularity, and the reduction of error propagation in the domain. So in that case, if you deploy only one neural network for entire domain, so the convergence will be controlled by the global error. But when you deploy the separate neural network for each subdomains, the convergence will be the controlled by the local error in the subdomains. So that's mean that you will converge faster than in comparison to one neural network. So just to be a little bit the abstract representation. So this is a typical PD, which is conservative loss defined by, so this is the rate of change of supposed density, and this is the flux, which is like have a spatial derivative. So this F is basically flux. So flux continuity means, so suppose you have a two elements, that suppose this is triangle, and these these sides of the triangle are the stitched together. So in this direction, normal to this edge, your flux has to be continuous. That's why I have written here the flux taking the dot product with the normal in the outward direction of this edge, and then the similar for the neighboring element. So it's basically across the interface, the flux. This says this the flux continuity is basically the across the interface in the normal direction, your flux has to be continuous. And in that case, you have to impose another continuity condition on the solution. So suppose you have a smooth solution, so you can take the average, and it will be here at the interface giving the, so if this is the green vertical line is the interface, so on either side of that, you have a solution, and take the average, it will give you the unique solution. Suppose you have a shock, again, it's kind of row type of approximation for the shock. You take the average on either side of interface and just impose that the continuity is, the discontinuity is approximated in this way. So this is for the flux continuity. And this is only applicable for if your domain is convex, it's regular shaped. What happens if a domain is non-convex? So to overcome this, we have XPINN. So what we do here, rather than the flux continuity, we directly impose the residual continuity across the interface. So this is very generic representation, because here you don't have to compute the normal along each faces. So, but this that can be directly achieved by imposing the residual continuity on the interface. So that is also called the XPINN, the extended pin. And if you want to implement it in the parallel, how you will implement these approaches in the parallel programming environment. So you can see that for cPINN loss, you have two loss function, which is the data loss function and residual loss function. They are embarrassingly parallel. You don't need any communication for them. And for the residual, for the flux continuity at the interface and the solution continuity, you have to have the communication from the neighboring subdomain. So there are these two losses which you will require the communication from the neighboring element. And similarly for XPINN also, here LFI is not the flux, although it is residual, but the communication model is same. Yeah, like for both the solution continuity and residual continuity, you need to require the communication. So this is the just in for the sake of completeness in comparison data and model parallel. You have a domain. Now we don't have data here, just domain is split into suppose 4 parts. You have 4 GPUs, and each subdomain have a different neural network. You can have different neural network. It doesn't have to be same. Because of because we are imposing the continuity through some physics, and here you compute the loss for each GPU or each subdomain, and then you just share the solution at the interface through the neighboring element in a point-to-point using the point-to-point communication protocol. That's it. There is no collective communication which you require from each GPU to all the GPU going to the single GPUs. So in that way, your communication cost will be very constant, means whatever the number of GPU you use. And then again, the last 2 steps are similar to the typical neural networks, like updating the neural network, so where you compute the gradient of the loss and then update the parameters. So this is very simple approach, and this is also the domain decomposition approach in the finite element at the finite difference we use. But rather than there being the element, here we have a data points. So we don't have to use the parameters or matrix or graph partitioning algorithms for them. So because we are satisfying these conditions at the point, not on the elements. So just for an example, so we just took the steady state Navier-Stokes equation to solve for the lid-driven cavity. So here we just took this equation. We don't have time derivative. We have nonlinear term here. And then you have a pressure term, and then the diffusion term. And here the continuity equation. So we just took this and we split entire domain in the 12 subdomains. So here the triangle basically represents the residual point in each subdomain, and the green square represents the interface points. So interface points doesn't require to be very large. It can be very small depending on the regularity of the solution. There is no thumb rule that how many points you need to have at interface. So you can choose it randomly. You can change the equidistant. It doesn't matter. And if you want to write into the processor's layout, so it's a typical, like if you have this subdomain, although this subdomain doesn't have any data because it's interior of the domain, it doesn't conform with the boundaries, because here our only data is the boundary conditions. And here for this subdomain, you require 4-way point-to-point communication from the each edges. And for here, the corner element, you just require the only 2-way point-to-point communication. Okay, so this is the very feasible the programming model for the MPIs. So we just implemented that. So before I go and show you the scaling, I just did an accuracy check with the existing solution. So this is the horizontal velocity, the left one and right one, and these are the the cross section of the velocity along this vertical line, the green vertical line, and overlaid with the solution, reference solution, which was taken from here and here, that they have published the solution of this kind of problem for many Reynolds number. And similarly for V, they matches very well. They match very well and have a very decent agreement with the reference solution. So what I did here, I just measured first on the CPUs, and I increased a lot of points on the interface so that communication is high. So the size of the buffer is very large, so that we can know that if communication time across the CPUs are constant or not. So here we have, like, I went up to 24 nodes. This study was done at the summit that the Oak Ridge National Laboratories, the IBM machine, and you can see that the communication time is pretty the constant, and the compute time is only for computing the residual loss and interface loss. And this is for cPIN, and this is for XPIN right side. You can see that for XPIN, it takes more time than the cPIN, because when you do the cPIN, so you have a flux. So that means you have a one derivative order less to compute. And that means you have a one order less for the communications. So that is the reason why cPIN is fast. But for XPIN, it's basically computing the PD, but at different point at the interface. So that is why the compute time for the XPIN is larger. And similarly, this is for GPU. So GPU also, we observe the same pattern. The cPIN has less time than the XPIN, and the communication time across the number of nodes. So the x-axis is number of nodes, and each node have like 4 GPUs. And here you basically here I just increase the number of compute number of the points inside the domain, because of the GPU to GPU communication is larger than the CPU to CPU communication. So that I can hide that latency with the flops actually. So that's why you will see the compute time here is more than the communication time. And similarly for XPIN, because for the production run, we are not going to run any problem on the CPUs, because these problems are large, so the larger in the size, so CPU will not perform as good as GPU. So we can see that, and this is just in terms of the weak scaling. So as number of nodes and number of processor increases, workload also increases proportionally, and it achieves very decent the weak scaling for the cPIN and XPIN. And as I said, why communication time is more in XPIN? Because when you compute the flux cPIN loss, so suppose for this, suppose you take the continuity equation, and here if you have to do the cPIN, so you don't have to compute the derivative. Only solution has to be communicated across the sub processor, across the processor. But if you do the XPIN, you have to compute this, and you have to communicate with the solution as well as the gradient of the solution. That's why you have a more compute and more communication. That is the reason why XPIN is slightly expensive. But yes, we have also tested that since cPIN can be decomposed into the space, but XPIN doesn't require this kind of a constraint. It can be decomposed along the time also. So I have one slide that how the performance gets better for XPIN if you decompose along both space and time. So this is the weak scaling. I just did up to 24 GPUs because I had access to only 24 GPUs maximum, and we just matched the weak scaling is very close to the observed weak scaling is for XPINN is very close to the ideal one, and but here you just for 24 GPUs, the number of points here, since we don't have any images, which I can say that images per second that, but here we are doing everything on the point. So we can have almost 1.5 into 10 to the power 5 data points per second. But for cPINN, that is large because in the same time we can do the more because we don't have to do a lot of communication or the more computation in terms of the computing the flux. So there was the hackathon at the Argonne, and they took our code and they just wanted to do the weak scaling for more GPUs. Like they had theta GPU, so each node have 8 GPUs, and they have like 16 nodes they gave us, and we tested that up to 128 GPUs. This scales perfectly. After that, we did not have access for number of GPUs were limited up to 128. But after that, we got some allocation, ALCC allocation, and we have tested this algorithm for 1024. That is a GPUs, which is a LES problem, which I will explain later. And also there are some optimization like accelerated linear algebra iteration, the compilation, XLA compilation for the code, which also increase the efficiency. So time of per iteration goes down so significantly if you use XLA and those the just-in-time compilation approach. So the one problem where the first paper was published, that we took a larger problem. What we did, we took entire United States map and split into the 10 regions, depending on the heat, how much summer, how many months of summer they face, and how the heat and conductivity is in across the US. And we wanted to solve this conductivity, the conductivity PDs, heat transfer PD, and here we have to compute the K, which is conductivity, and T is only given at the boundary of the maps, the map only at the boundary, and we wanted to reconstruct the conductivity in entire region. And here right side you can see the black points are basically the interface points, blue points are the residual points in each subdomain, and at the boundary we have a boundary conditions. And with that, the good thing about PIN is that you can solve the forward and inverse problem in one shot. You don't have to run it separately and update, because the K can be defined as a trainable variable, and you can solve for T and K together. So with this setup, so you can see that at different in 10 subregions, we have a different residual points depending in the size of the states or size of the region. So suppose here this one, this has a small, so this is small subdomain, and here we have a less residual points, and we have a neural network of only 2 layers or 3 layers. So these kind of things you cannot do with the data parallel approach. But you can, just imposing the physics, you can do it through the cPINN or XPINN. And so here the left and top, the left top figure is basically temperature predicted just from the boundary data, and this is the right top figure is the conductivity, and the bottom top figure, left figure is the error, which is of order of 10 to the minus 3. And the right one is also the error for the conductivity. So it recovers very nicely up to the significant amount of the accuracy. And this is the problem which we solved, and this is the largest problem we solved in that particular work. But after that, we extended it for the fluid problem, but which I will discuss later. But before that, just wanted to show you the scaling. So I just did it both. I did it both CPUs and GPU. So the left one is for CPUs. So there were 10 subdomains. So I just took 10 cores. The first pair of the bars are basically 1 CPUs, and the blue bar is basically to when you consider only float 32, because these PDs are very sensitive to this float 32, float 64, and they have shown that a lot of substantial differences in the accuracy if you choose the float 64 in comparison to float 32. But yes, you have to pay the price in terms of the wall time. So you can see that for a float 32 takes around 5 hours, and float 64 it goes up to 12.5 hours on CPUs. But if you use 10 CPUs, it goes down to like the 10 CPUs. If you take with the float 32, it's primarily taking the 1 hour or something, and the 10x. It's almost 10x in comparison to float 64 because it takes more time to compute. But most of the time is spent here in the communication. So the compute is not the resolution points are not allowed. So the most of the times while increasing the 1 CPU to 10 CPU are taken in the communication. Similarly, we did it for 10 GPUs. So 1 GPUs, you can see there is like almost 9x speed up we get. But I have checked that most of the work for the 10 GPU, most of the work done by the GPUs is just it's a kernel latency, actually, that's it. And that's the computation is done very quickly. So most of the time is done, it is spent on the communication. So this was scaling perfectly. So we got motivated and we took, we just, before I go into the much larger problem, I just wanted to show that how we can reduce the time for XPINN. So suppose this is the x-axis is the t and y-axis is the space, that is xt. But for cPINN, you can only decompose into space. So there are 4 spaces. But for XPINN, because the flux is only computed in space. But for XPINN, you can decompose into the space and time together because it computes the residual on the interface. So you can see that with this cPINN takes 0.14 second and the XPINN is exactly half, like 6 seconds, because now we have more subdomains and more number of processors. So that's how the XPINN time can be reduced. So after that, this is the ongoing project, and we have finished up to substantial extent, but we have to run few more tests in comparison to CFD solver. So what we are trying to do, we took the Navier-Stokes equation, and our database is basically Johns Hopkins Turbulence database. So all the data we process from that data hub, and we filter this Navier-Stokes equation. And to compute this is the basically LES modeling, large eddy simulation modeling, and we need to compute the subgrid stresses. In the subgrid stresses, we used a Smogensky model with Van Dries damping. So that is given by this equation, the stress. And idea is to compute the CSY as an inverse problem for this approach, because CSY, the CSY at the wall has to be 0, but in CFD solver, it is never achieved. But in PIN, we want to see that if it can achieve 0 at the wall, and how does it varies when we change the grid size of the filter data. So in nutshell, the objective for this work is to compute this 1 plus delta C. So from wall to central line, how delta C varies, the correction in the Smogensky constant. And for that, what we did, we took the 2 neural network. One does one computes the solution of the Navier-Stokes equation, and this delta C, which is only dependent on Y. So the space, the input space for delta CY is only Y, it doesn't depend on T or X. So it's from the wall to central line. And for that, we used another neural network, and we just plugged that in the original Navier-Stokes solver. And you receive the loss, which is made of the data loss, which is the boundary and the initial condition, and the physics loss, which is just exactly the filtered equation, filtered Navier-Stokes equation. And this is the glimpse of the data size. So for each time steps, we have almost 200,000 data points, and there are 4 fields. So and for one time step, we have close to 1 million data points, and we wanted to do it for larger time integration, which is 1024 time steps. So it was a very large data sets, and we can't do it on the serial or the 1 CPU or 1 GPU. So we have to go on the multi-GPU. But how would you check the accuracy of the solution? Since we have a DNS data, so it's just, we wanted to show that how the CSY varies. So we can do an a-priori testing because we have a DNS data. And from there, we can compute this dissipation rate, the exact dissipation rate, and from Smogensky also, which we compute from the XPINN, we can also compute the dissipation from there and take the ratio. and that has to be close to like 0.1 or 0.11 or something like that. So we did it, and what we did, we took 1024 cubes, 1024 GPUs on Polaris, and 800 nodes, and one node has a 4 GPU. We tested two architecture, the data parallel, where we don't do the where we don't play with the physics, but in XPINN where the solution continuity is imposed through the physics. So you can see that left one is the loss function. So loss function goes up to 10 to minus 4. This green line is the mean loss function across all the 1024 GPUs. So you can see from here that each GPU, each cube, like solution at each time step converges differently. So that is why you see that the standard deviation is pretty large. Here, the right side is the green one is the XPINN computed CSY, and the red one is data parallel computed CSY, and black one is the reference. So they matches very well, and they match very well among themselves. And at 0, which is close to wall, we achieve the CSY to be 0, which was not the case for the CFD solver. So with that, you can see these are the field. This is a stream voice velocity. The error is of order of like 10 to the minus 2. So the left one is the actual, middle one is the predicted by the XPINN, and the rightmost one is the error point-wise, computed point-wise absolute error. Similarly for V, the instantaneous velocity V, the vertical velocity, and then you can see the error is almost, the dominant error is close to 10 to the minus 2. And similarly for W, the another component of the velocity, the error is again of the global error is almost 10 to the minus 2. So we tested many architecture to see how XPINN performs if we increase the number of GPUs or the number of the cubes along which we are splitting it. So here we split along one time step is one data sets, one subdomain, another time step is another subdomain. So you so this one XPINN, when I had 128 GPUs, and each GPU have a 4 timestamps, so it is 5.87% error. But if I increase it to the larger number of GPUs, so it goes to 1.53% error, because now one neural network is to approximate one time step. Earlier, it was like one neural network to approximate 4 time steps. So that means as you increase the number of subdomains, your expressivity also increases, and therefore the error reduces. So this was the general trend we observed, which goes again in parallel to our understanding of these models. And with that, this is the this study which I just performed the last week. So there could be some more the detailed fine-grained level of profiling I need to do. But I did up to 1024 in weak scaling sets. The leftmost is the time taken by one batch, because I kept our batch size fixed so that there is no biasness in computing the time. So and I ran the same batch 10 times, and this the compute time is averaged over 10 times. And the wing scaling up to 1024 was very nicely achieved without almost I got 99% efficiency. But I haven't done yet how much time is compute time, or how much time is the how much of these bars are invested into the computation and how much in communication. And then again, I did that how many data points they crunch per second. So it's like close to like a 10 million for 1024. So it is showing a very good agreement with the ideal XPINN if you run on the one GPU. And right one is the efficiency. So basically, I just divided the compute time, the total time with number of GPUs. So almost 99% efficiency I have observed. Up to 1024. I don't have access more than I don't have access GPUs more than 1024. So I was just limited by that. I just wanted to see where this breaks actually. So, but I was unlucky up to 1024 even GPUs. So with that, like the conclusion is that for these kind of scientific machine learning approach, data parallel will not be sufficient, because data parallel, you don't increase, you don't include the physics in there, and data parallel will have a more compute time because it performs two collective communication, whereas XPINN and cPINN, they have only point-to-point communication, and that communication cost is pretty much constant. And the same code can be used without any changes on the CPUs or GPUs. So we have two versions of that in TensorFlow and in the JAX. So for JAX, it is very easy. I did with the MPI JAX, but there was some way to get around the point-to-point communication, but we were able to figure out with NVIDIA's new the singularity image for JAX to run over the multi-node and multi-GPU type of architecture. So, and because we don't have a lot of data, but we have a lot of high-dimensional data, and we perform the automatic differentiation. For this approach, we use forward mode auto differentiation for residual computation, which does the Jacobian vector product, and then do the push forward. Because for this dimension is so large, because reverse mode automatic differentiation will not be efficient for that. So there is one thing we want to work a little bit more, like how to make this kind of API to be picked automatically. So these were our experience, and with that, I will like to acknowledge our sponsors. So all this work were sponsored by the Air Force Office and the DARPA, the Compound project, and our local cluster at CCV, which is called Center of Computation and Visualization, and then ANL's ALCC, that allocation programs, which we have till August. So these are all the challenge problems which we were dealing with. And with that, I would like to thank you and thanks for hosting me. I will be gladly take any question if there is any, and also the suggestion if you want me to test some other things. You have some other APIs which have come across which can do the ADs much better than existing implementation. I will really appreciate. Thank you.
Thank you very much. Thank you, Raj. So let's look at the questions in the chat. Maybe the first one would be the request for from Sagnik to maybe share. Maybe you can do that in the chat. I don't know.
Yeah. Sagnik, yeah, I can explain the Sagnik. Their question is, what is the flux essentially? The flux is basically, if you want to see the mathematically, in any conservative PD, the term, if you take out this one order of spatial derivative, so the flux has to be conserved. So suppose you have a, if your density is, suppose your fluid is flowing and if it goes across a cross section, so the amount going in and out, that should be the conserved. So that is the flux, which is the spatial derivative in the PDs. So that basically ensures that your flux is the flux is conserved, and therefore the quantity of interest is conserved. So if you see suppose take an advection equation ut plus aux. So what we are trying to advect here, au is the flux, basically the speed and the field of interest. So that is the flux going across the cross section and the coming, and by you taking the spatial derivative, make sure that it is continuous. So that is the flux.
And Sagnik also asked if you could share links or DOIs to the publications you wrote.
Yeah, sure. I will just
thinking maybe have a second,
yes,
drop into the chat.
Thank
you so much. Thank you.
So let me drop that just a moment.
Yeah, and there was another question regarding the materials. So
Okay.
we will share them. We'll send folks. I guess the folks who registered the direct link.
Yeah. So I just pasted the paper on the chat box. You can have a look there. Yeah. So next question is, have you encountered models that differ across domains in numbers? Yes, this the alias problem, we have a different numbers in each subdomain. So you know that, let me show you something. So here, so let me show you that one thing I think I missed. So the first time is 64 GPU, and I just took 64 time steps. So there are 1024 time steps which are trying. Up to 64 time steps, you have less than 1% error. But when I took 1024, I have more than 1% error, because up to here there is no turbulence. There is no separation, no turbulence, no vorticity. So that's why when we are in the middle, like because we know this database, so we know that it is a channel flow problem. So we know that during the 256 to 1024, we have more turbulence, more chaotic. So you require a strong neural network to approximate. So that's why we have changed the model after certain time steps where your solution become more chaotic. So that is what we did for having different model for each time step. So I hope that answers the question. So
there's one from Roland Haas. I don't know if you see it.
Okay.
About high Reynolds numbers.
Yes, this work we did with the Reynolds number 1000. This channel flow problem, RE tau is the 1000. But for high Reynolds number for PIN, you may want to learn the gradually, because you learn for 100, then take that solution and then take that weights and bias and then go for the training for the Reynolds number 200. But for forward problem, it will be a challenge going for the higher Reynolds number. But for inverse problem, I think it will be the one of the best methods. Suppose you want to compute the from a given data. So we have a lot of work on the AIV, PIV, if you know that the particle image velocimetry and all those. So suppose you have a 2D snapshot and you want to recover 3D field. So that we can do with this. And suppose you want to compute some Reynolds number for a given flow, you want to compute some parameter. You have a couple system like the heat conduction, heat transfer, and the fluid flow together. So there you want to compute the Perslate number, something. So for inverse problem, it will be a very good tool. But forward problem for high Reynolds number, we are also working on some other methods motivated by the conventional fluid dynamic CFD approaches, like the separation of the field, tensor product, and all those. But as of now, I think I did cavity flow up to Reynolds number 400. After that, I had to do a lot of, it was hard to convert more than Reynolds number 400. So that was it.
Another question asks if any of the codes are available online.
Any of what? Yeah. Means this code, like I can make it available. Like if you want, I have a private repository because I have made it public, and I started getting so much the spam mail from the Git bot, or somebody played nasty with the GitHub. So I have to make it private. But if you want, I can share with you.
Yeah, maybe Amar Sagar, you can just send your email.
Yes, I can send it to you. So yeah, if you want, just please feel free to write, because after that I started sending the code through email because it was so much spam in my email. So there was so much. Yeah.
And the final question from Rahul, I don't know if you see it. How does, yeah, you can see it, the time decomposition versus.
Yes, so that is what I showed, like your XPIN you have to do more computation and more communication. Because when you take cPINN, so flux when you do, so you can get rid of the first order derivative. Like suppose you have a partial u by partial x as a flux, so you don't have to compute the derivative partial by partial x. You just have to flux will be u, so you don't have to. So that is the one thing. You can get rid of cPINN, but suppose you have a non-convex domain, so cPINN will not work. So I would suggest if you have a very regular domain, convex domain, so go for cPINN. It will be much more efficient. If you have a non-convex domain, like we usually encounter in the solid problem, like the L shape, the very famous toy problem, the L shape is to solve the stress on that kind of domain, you have to consider the XPINN. So
okay,
so yeah.
Maybe two more questions we've seen. One from Eric. If you want to.
Yeah, so Eric Vessel, here you looked at splitting the domain differently, but I found it interesting that in the limit of the trivialities. Yes, yes, but the only difference is that in the finite volume, you do compute the solution at the cell center. Here, most of the solution are point-wise solution. The first thing. Second, the PIN and in total PIN and XPINN, these kind of approaches don't need meshing because we are just sampling the residual point randomly in the domain. So think about how you fuse the experimental and numerical data. So because experimental data is acquired like at random sum points, and to compute to have like to do the forward inverse problem, you need to compute the solution point-wise. So that is one good thing about PIN, that you don't need the meshing. But yes, that's why I said the finite volume. So if you marry the finite element and finite volume, it will become discontinuous Galerkin. So that's why I said this has a parallel with the discontinuous Galerkin approaches. So yes, you're right. It's very close to the finite volume method, but we compute the solution at points, not at the cell center. So that's the only difference.
Okay, let's address the two last
Yes.
questions.
Yeah. So this question is very interesting. It was one of the questions from the reviewers also, that did you compare the performance of first order? Okay. So here is the thing. So LBFGS doesn't work for the batch training. You have to have single batch to do the LBFGS training. You can't use the LBFGS in this way, either for the Horoward. If you know the Horoward, the Uber API for data parallel, you have to do the optimizer. You have to choose single order, because LBFGS, actually it is LBFGS, but we are not computing the Hessian. Hessian depends, we are approximating the Hessian, and that depends on the previous memory-based computation, like how many iteration previously it has to go to compute the Hessian for the next time. So now you see that you can't use it through one batch, single batch training. So multiple batches, because they will have different data points. So that is the first thing we are not yet there, that how to do the LBFGS distributed like in the batch-wise training. We are not there. If you have any suggestion, we'll definitely consider. But right now, that is a block. That is a block for using the higher order the optimizer. But if you have a like simple problem like Burger's equations, you want to do the forward base, you want to just do the forward simulation. Yes, because the data is small for them. Like initial condition is very small. The data points are very small. Boundary condition is also small. You can LBFGS, and but you can't start with LBFGS. You have to run through some ADAM epochs before you kick in the LBFGS. It's because of the regularity of the loss functions.
And final question from Sagnik.
Yeah. So, are there ways to speed the training steps for a given one? But yeah, I'm not very well aware with the reduced order model. But my master's advisor, Professor Hesteven, he was working a lot on that. And I think for the dissipative problem, like fluid problem, yes, reduced order model is good, but the only problem is that they don't generalize well. Suppose you change the domain and you have some means how you sample the parameters. For system, it is always a problem, like a system of equation. But for hyperbolic problem, I haven't seen any reduced order model which is very successful. So these are two. Maybe I have not kept up with the recent publication, but till last year I've known that for there is a one work by the Kevin Karlberg from Sandia, and he did some theorem and he proved that why it is difficult to have a reduced order model for hyperbolic system. And in terms of the neural network and reduced order model, so you know the reduced order models are linear basis functions, because you take the snapshot of all the solution, gather it as a column, and then take the POD. So that is pretty much like the linear basis function. But for here, neural network, we have a non-linear basis function before the last layer. So that's the only difference. But yes, that will be, those are some open questions we haven't answered yet. So
Thanks.
Okay, well, thank you very much, Raj. Thanks everybody for attending. And like I said, we will be sharing the slides, and hopefully I'll stay in touch also with Raj and with each other.
sure.
Thank you.
Thank you very much. Thank you. Bye.